Picture this. You've got an infinite grid, just floating in space, stretching endlessly in literally every direction. Now imagine we're populating this grid, not with boring mathematical dots, but with glowing cosmic everything bagels. Our goal for this explainer? We're diving into a mind-bending discrete geometry paper by mathematician Anubhav Gosal, perfectly titled A Note on the Extensible No 3-in-Line Problem. This paper takes a classic, century-old math puzzle and just stretches it to infinity, literally. So buckle up because we are about to explore a seriously fascinating blend of random probability, rigid geometric constraints, and the infinite void.
Now, to really understand the infinite, we kind of have to start small, right? Let's rewind a bit. Over a century ago, a mathematician named Dieudonné posed this famous problem. If you have an n by n grid, what is the absolute maximum number of points, or, delicious everything bagels in our case, that you can place on it so that no three ever form a straight line? This is known as the no 3-in-line problem, and it's an absolute legend in discrete geometry. Think of it like a massive cosmic game of tic-tac-toe, where getting 3 in a row is exactly what you are trying to avoid no matter what angle you're looking from, horizontally, vertically, or diagonally.
Okay, so what's the absolute limit to this puzzle? It's actually surprisingly simple. The trivial upper bound is exactly 2n. And why is that? Well, think about the vertical lines on your grid. If you place 3 bagels on the exact same vertical line, boom, you instantly break the rule. So you can at most put 2 bagels on each of the n vertical lines. 2 times n gives you 2n. Interestingly enough, this super simple observation is still the best known upper bound for this problem. Mathematicians have known for a long time that you can get pretty close to this 2n limit on finite grids, using these incredibly complex structures like modular parabolas to pack the bagels super tightly. But what happens when the grid never ever ends?
Well, this brings us to Joshua Erde. He introduced a complication that turns a fun little puzzle into a massive mathematical headache. Enter the extensible version of the problem. We aren't just looking at a fixed, finite grid anymore. The grid is now an infinite lattice, which mathematicians denote as z². And here's the kicker. The extensible rule states that as we zoom out to larger and larger n by n sections of this infinite grid, our bagel layout has to remain permanently locked in place. You can't just rearrange the bagels you've already placed just because the grid got bigger. The layout must be perfectly consistent, all the way to infinity. This constraint completely changes the game. The intuition used to be that you couldn't possibly get a densely packed infinite grid this way, because historically, finite solutions depended heavily on the exact size of the specific grid you were working with. So you might be wondering, just how dense can this unchanging, infinite bagel universe actually be? Let's look at how the math boundaries have shifted. Previously, an older limit was proved by mathematicians Nagy, and Woodruff. They managed to pack bagels at a density of omega n divided by log to the power of 1 plus epsilon n. They pulled this off using a really structured, greedy approach, carefully deleting triples along very specific mathematical curves. But Anubhav Gosal's recent paper? It completely shattered this. His new limit is omega n divided by the square root of log n. Now, I know that just sounds like a bunch of math jargon, but in the world of asymptotic geometry, dropping that exponent down to a square root is an absolutely massive, tangible breakthrough. He bridged a huge gap. But how exactly did he do it?
The answer is beautifully, almost hilariously, counterintuitive. Gosal didn't use some strict, highly orchestrated geometric blueprint. His big secret? Well, as he states right in his paper, our construction is random. Yeah, you heard that right. To build a perfectly rule-abiding infinite grid that maximizes density, the absolute best mathematical strategy is not to place the bagels deliberately, but to literally throw them completely at random, following very specific statistical rules, of course. It feels almost paradoxical, doesn't it? Injecting randomness into a hyper-strict geometric constraint actually yields the tightest known structure. Let's break down exactly how this random construction works.
Gosal's method can basically be boiled down to a totally logical 3-step sequence. Step 1, toss the bagels onto the infinite grid using a very precise decaying probability curve. Now, because it's a random process, you are inevitably going to make mistakes. So that leads to Step 2, scan the infinite universe and identify every single accidental line of 3 bagels. And then Step 3, which is honestly the genius part, resolve these rule-breaking triples by systematically deleting the bagel that is positioned furthest out from the center. This deletion method guarantees that no 3 bagels form a line, sure, but it also ensures that the inner core of our grid remains as densely packed as mathematically possible. Let's look a little closer at that probability curve from Step 1 because that's where the magic happens. This formula right here, this is the secret sauce of the entire paper. This curve determines if a bagel randomly lands, and actually stays, on a specific grid coordinate. Let's call that coordinate x. The probability is essentially a small constant, c, divided by the infinity norm of x, multiplied by the square root of the log of the infinity norm of x. Now actually, scratch the fancy jargon for a second. The infinity norm is really just a math term for how far out the point is from the origin, shaped like an expanding square. So, in plain English, it simply means that near the center of the universe, bagels are highly likely to appear. But as you travel further out into the void, that probability drops off at precisely the exact rate needed to balance the density against the risk of forming accidental triples. Now, to mathematically prove that this random probability actually works, without accidentally deleting everything and leaving the grid empty, Gaussal had to somehow organize this infinite void. He did this using a few key geometric concepts. First, we have dyadic shells. Imagine these pulsating square rings expanding outward from the origin. Gaussal groups the grid into these expanding shells to calculate how many bagels land in each specific zone. Second, primitive vectors. These are essentially fixed, unoriented directions across the grid. And third, lattice lines, running along these exact directions. By analyzing the expected number of random bagels falling onto any given lattice line within those dyadic shells, Gaussal could mathematically predict exactly how many accidental three-in-a-line clusters would form. It's kind of like calculating the expected rate of cosmic traffic jams.
Okay, so once he knew how many accidental triples to expect, he applied that crucial final step we mentioned earlier, the deletion method. Whenever three bagels accidentally form a line, you don't just zap any random one. You absolutely must delete the bagel with the largest infinity norm, meaning the one that is physically furthest away from the center of the grid. If there's a tie, you just break it arbitrarily. Why does this specific detail matter so much? Well, if you deleted the inner bagels, you would completely hollow out the dense core of your universe. By always sacrificing the outermost bagel, Gaussal protects the high density of those inner expanding shells. He mathematically proved that the random bagels landing in a shell will comfortably outnumber the bagels you are forced to delete from it. And that careful, brilliant balancing act is exactly what leads to the triumphant reveal. Because the random spawning rate safely outpaces the necessary deletion rate, the surviving bagels form a strictly no three-in-line set that successfully achieves that massive new lower bound we talked about. This single random construction shattered the old record, improving the density by a factor of the square root of log n. It proves, without a doubt, that you can indeed have a highly dense, permanently fixed layout of our cosmic bagels stretching into infinity. And amazingly, carefully tuned randomness is currently the absolute best tool we have to build it.
So what does this all mean for us? What's the big takeaway? Gaussal's paper is just a stunning demonstration of how probabilistic methods can solve incredibly rigid, infinite geometric constraints. But hey, the mystery isn't completely solved yet. We bridged the gap by a factor of the square root of log n, but there is still a noticeable distance to that trivial 2n upper bound we laid out at the very beginning. Gaussal himself even notes that it's plausible to improve this slightly with even more complex random processes, but closing the gap entirely? That would likely require wildly new mathematical ideas. So what random process, or entirely new geometric concept, is going to finally close the distance to that ultimate 2n limit? That is the next frontier of this cosmic puzzle, and it certainly leaves us all hungry to explore further. Thanks for joining me on this explainer.